Hello everybody, greetings from Chile, South America. Let me introduce myself. I'm Giovanni Salini, PhD in Physics, and I work at Applied Mathematics and Physics Department, Universidad Católica Santísima Concepción, in Concepción, Chile. My colleague is Dr. Pacheco. He works at Physics Department, Universidad Tecnológica Metropolitana in Santiago, Chile. Our talk is titled Probable link between COVID-19, particulate matter, ocean, and some meteorological variable in Santiago, Chile. Some questions we will try to answer here, such as, is there any link between environmental pollution and coronavirus, or are there other factors that are not be considered? In this talk, we want to present a study on the possible spread of the COVID-19 pandemic among humans through aerosols contained in urban air contaminated by respirable particulate matter and Superferic Ocean. To show the incidence of meteorological of the boundary line in the spread of epidemics in an area where its associated morphology has basin characteristics and pollution prevail over time. For it, our objective was to study the possible link between pollutant and tropospheric weather, including the possible connection with the high population density in small places. We point out how the physical sciences through thermodynamics can contribute to the analysis of epidemic spread. Thermodynamics is focused on processes in equilibrium where determining reversibility and order work according to what is expected. However, it was Pacheco who discovered that for the equilibrium, new structures appear spontaneously. Specifically, from chaos, other structures arise that require part of energy for their conservation, not having a linear character. Then they will be difficult to predict. Our study hypothesis is if a virus enters the human body through the respiratory tract, then its connected urban meteorology favors the sustainability and spread of pollutants, making the infection, cultivation, and spread of a virus more effective. Here is our data from monitoring station at Santiago, Chile. The study period was 2.5 months from March 13 to June 15, 2020. That is during the first wave. 7 communes were chosen at random. They obey no a priori epidemiological criteria. That is, there was no intentional selection of data. The data recorded in the form of hourly time series of 3 variables were considered: temperature, relativity, humidity, and wind speed. The 3 pollutants, PM2.5, PM10, and Superferic Ocean, were considered in the period of corresponding to autumn-winter in Chile. The meteorological and pollutant data were extracted from Chilean air quality system. The accumulated SIG data were extracted from Chilean Ministry of Health. The hourly accumulated SIG data recorded for each commune studied present the typical statistical graph for this type of data over time. Furthermore, they show they don't present chaotic form. Particulate matter in environment reduce visibility, affect vegetation and human health. On the other hand, Superferic Ocean is a powerful oxidant, produce adverse effects on human health. The reason for choosing this contaminant is because they are known to affect the human respiratory system. Time series of temperature, relativity, humidity, and wind speed were used because they allow describing atmospheric process and thermodynamic associated with it. In Table 1, we can see some statistics about population and accumulated 6 by commune. In this table, we can see strategies applied to attack the emergency due to COVID-19 in Chile since the pandemic began until now. In this figure, we can see the number of confirmed daily cases from the beginning of the pandemic at March 2020 until now, May 3, 2021. Our methodology used here was the analysis of nonlinear time series. If the epidemic, environmental pollution, and local meteorology are considered as a complex system very sensitive to unexpected initial conditions like a new virus, an analysis can be made from nonlinear analysis and chaos theory. Such an analysis was applied to this time series considering the following parameters for the quantitative measurement of chaos: Lyapunov exponent, Hertz exponent, correlation dimension, Kolmogorov entropy, and Lempel-Zip complexity. All these parameters allow to determine if the system is deterministic, random, or chaotic, with interpretation of this parameter considered below. Also, Lyapunov exponent, Hertz exponent, correlation dimension, and Lempel-Zip complexity has interpretation. Each one of them has its point out here. New time series was constructed from the hourly Gaussian using the meteorological and pollutant variable measured in each commune, already proven to be chaotic, has the denominator for the hourly record of AS according to commune of tiny 42 new time series, each one consisting of 1872 hourly data, being AS hourly accumulated 6 for each commune. From the epidemic perspective, the number of infected patients was linked to the hourly time series of meteorological and pollutant variable generating new time series. To do this, the effect of the virus is quantified from patient accumulated over time and from meteorological variable and pollutant through entropy. This would indicate the ability to spread disease. To demonstrate our hypothesis, the chaos theory was used, in which the system is considered as a dissipative structure. From the epidemic perspective, the number of infected patients was linked to the hourly time series of meteorological and pollutant variable generating new time series. The chaos theory formally is applied to this new database to obtain the Lyapunov coefficient, correlation dimension, Kolmogorov entropy, and Hertz coefficient, showing good agreement between meteorological pollutant and accumulated 6 variables starting from entropy. The value of the parameters were correlation dimension DC less than 5, Lyapunov exponent lambda greater than O, Hertz exponent H with range 0.5 less H less 1.0, Kolmogorov entropy SK greater than O. Additionally, the Lempel-Zip complexity LZ greater than O, which indicates chaoticity. From table 2, it can be deduced that the Kolmogorov entropy of the pollutant is greater than the same sum for the meteorological variable in all the commune. In the same way, are more complex when comparing the complexity Lempel-Zip of in table 2. From the table 2, we can see chaotic indicator for the time series under study. In this figure, we can see entropy grow, then increasing trend of persistent loss. In figure 5, we can see increase in accumulated patient per commune versus total entropy. The chaotic test method applied to this time series showed that all of them present chaos. Then hypothesis was demonstrated. Also, meteorological and pollutant variable do dissipate a pandemic by increasing its complexity. From the entropy, a good agreement was found between meteorological variable, pollutants and the number of accumulated patients. This shows the ability of pollutants to create an artificial urban climate over a natural one. To this is added the low ventilation capacity offered by the wind. Also, it is the most entropic compared with the other meteorological variables, due to the modification of the roughness of the surface due to the increase of the building in height, favoring the urban canyon barrier formation to the flow of wind and thermal island. The foregoing shows that an artificial dominated by pollutant, closed and poorly ventilated environment increases the probability of the pandemic spread, has actually happened in the 7 communes for the period study. In this figure, you can see the thermal island in winter period. Relation through quotient X, Y, Z. This link favors and sustains the accumulated growth of infection and pandemic spread. See Table 3 and Table 4. In this figure, we can see that total entropy versus accumulated illness, then gradual increase in the entropy of pollutant emitted in the atmosphere acts comparatively with meteorological variables, further increasing the sustainability and spread of the pandemic. In this figure, we can see that the entropy is increasing when we plot total number of sick by commune in the study period versus entropy. In this table, Table 5, total entropy associated meteorological variable and pollutant to accumulated patient by commune, then persistent series, past trends last in the future, which remain in the time. Also, lower entropy predisposition to disorder, implying favor the spread of the SARS-CoV-2 between each social island. We have found that there is a relationship between urban meteorology, heat island, urban canyons, and roughness. Environmental pollution could worsen diseases such as coronavirus infection, COVID-19. Our preliminary results show that the meteorological and air pollution variable may be part of the fraction of elements that give sustainability to the accumulated growth of infected patients and favor the pandemic spread, making the accumulated diseases curve chaotic and complex. For all time series, the Limpel set complexity turned out to be between 0 and 1, which is indicative of connectivity and chaos. Lyapunov, Grades, exponent, and Komorow's entropy were positive, which also shows chaos. The Herd exponent was found to be greater than 0.5 and less than 1 for all time series, indicating positive long-term autocorrelation. The correlation dimension was less than 5, revealing that the new time series constructed are not random. A system under an unlikely condition will tend to organize it toward a more probable condition, then increased entropy. Rather than overcrowding, number of inhabitants in a house and number of rows in the house affect the viral spread. In the following 3 papers, you can see more information about our methodology here applied using the DOI code. Thank you very much for your attention.